Okay, so we are going to be solving this problem. We have multiple questions here. So the person is in this pose and they're lifting or pulling with a 300 Newton force, which is at a 45-degree angle. So we are going to quickly draw the FBT. I'm going to ignore the wrist weight. Okay, and if you want to do that, you can account for that too. Okay, so this is the free body diagram I have right now. This force, the object is shown in the green box, and it's being pulled at a force of 300 Newton. It's being applied at a 45-degree angle. So I have also labeled the links 0, 1, 2, 3, 4, and so forth. So if 0x is going to be 300 cos 45, and this is roughly equal to 212 Newton. Similarly, we are going to solve the y component, and it's going to be downwards again. So the f0x is going to be 300 Newton cos or sine, depending on where you consider the angle, but it's going to be same because 45 degrees. So I'm going to just do sine 45. This is roughly equal to 212 newtons. Similarly, the f0y is going to be equal to 300 times cos 45, which is same as the previous one, 2 newtons. So we have these forces. So we are going to be solving for the first link, which is from the elbow to the wrist link to the one, and we can draw a body diagram for the same. This is gonna be 202 Newton. This is gonna be short 2 Newton. And now we're just gonna do the force balance in the x direction. And I've assumed forces x, Fpy at the elbow, and then m elbow. So we're just gonna do the balance. We have px 300 sine 45, but I'm gonna just say 202 Newton is equal to 0. So Fpx is minus 212 Newton, roughly. And then we're gonna do the force balance in the y direction. So we have a few forces here. We have the Fpy, and then we have the weight of the link itself, which is 24.6 Newton, and this is available from here. We know that it's 24.6 Newton. So I'm just going to write it down. And then we have a vertical force of 212 Newton as well. And that's all we have. This is going to come to 0. So Fpy is going to be equal to roughly 236.73 Newtons. And now we're going to do a moment balance. Summation of all the moments is going to be 0. Okay, we'll start with the first moment, which is m elbow. So there's going to be a moment due to this weight or the force of pulling, which is 300 Newton. And I had created this kind of a section of this line. I had created the perpendicular distance from the center of rotation, which is Cp. So for computing moment, we need this perpendicular distance from center of rotation. So what I'm going to do is our force is 300 Newton. If you look at this diagram, you can see that this is our point of rotation, and then this is how it's being pulled. So it's going to rotate in this direction. So it's going to be a positive moment. So plus 300 times the distance Cp. And in order to compute the distance Cp, we have to do some construction here. This angle is 45, and then we know that this whole thing is 60 degrees. So we know that this has to be 15 degrees. So in order to get the Cp, it's basically the sine component of. So if you have this length, and if you take the cos component, it's going to be this. The sine component is the vertical one. So we know the length based on our data. The length is 0.364. So 0.364 times sine 15. And then we are going to have a moment due to the weight or the mass of the link itself, so 24.6 Newton, and it's gonna be again trying to rotate it in a opposite direction this time. So 24.6 times the length or the distance to the center of mass, which is 0.157. 0.157. And this time we are looking at, this is where it's being applied. This is the center of mass location, for example. This is where we are applying this 24.6. And if we extend that such that it's perpendicular from the center of rotation, we can see that we have a 60-degree angle here, and we need this distance. It's trying to rotate it about this hinge at B. So this distance is basically this distance cos 60 degree. So we're just gonna do cos 60. That's gonna be equal to 0. And if we solve this equation, we can, so it's gonna be 26.32 Newton meter. Now we're gonna look at the second link. So we have this link B, D. D is basically the shoulder, B is the elbow, and it's at 100 degrees or 80 degrees from here. And then we are going to have equal and opposite forces, FPX, FPY, and M elbow. And we already solved this from the previous link. So we know all these values. And now we'll solve this problem in order to find the forces, FDX, FDY, the M shoulder that we have assumed. So really standard process, we are going to do the force balance in each of the axes. Summation of all the forces in x direction is going to be 0. FDX is going to be equal to FBX is going to be equal to minus 212 Newton. And now we're going to do the force balance in the y direction. This 29.9 is the mass of this link, again obtained from the data provided. And so FDY is simply equal to 236.73 plus 29.9, which is roughly 266.63 Newton. Now we're going to do the moment balance. So the M shoulder will be there, and then there's going to be a moment due to the weight of the link, 29.9 Newton, and it's going to try to rotate in the positive direction, so I'm going to add it to 9.9. I'm looking for this distance from the center of rotations, and that distance is going to be equal to this length, and then sine of this angle, which is 10 degrees. So it's going to be the distance to the center of mass, which is 0.152. Let me check. Yep, 0.152 times sine 10, and there's gonna be a moment due to this force FPX and FPY as well. So FPY is gonna again rotate in the positive direction, so I'm gonna add that as well. FPY times the link length 349, and it's again gonna be sine 10 degrees and then finally we'll add the component due to the FPX, and FPX is trying to rotate in negative direction. So we'll add the force FPX and the length of the link 0.349. This time we are looking for this distance EB, because this force FPX is trying to rotate about this point D, which is going to be equal to cos 10, and everything is going to sum to 0. The moment at the shoulder, which comes out to be about 114.32 Newton meter. Again, double check my calculations, but this is the method that you'll be following. So we have the forces and the moments at the shoulder and the elbow. All right, so another part of the problem is to find FC compressive forces in the lower back and then the moment at the lower back. So I'm going to start by making a free body diagram. This is what my diagram looks like. So there are a few forces that are coming here into play at this point D, which are exactly equal and opposite to the forces that we applied to the previous link. And we know all the values, FDY, M shoulder, and FDX. So what we need to do is we need to find two things. We need to find this moment at L5S1. And then we also need to find FC. FC is nothing but basically the component of forces along the link, the compressive load the link is bearing. That is basically these forces Fc. So we have this lower back, this is the M5, L5S1, and we have compressive forces Fc, shear force Fs, and then we have a moment being applied to this link, and that moment is being balanced by the forces by this muscle Fm. So you can compute all those things. Right now, this is the link that we are looking at here. So in order to find Fc, the simplest thing we can do is we can take these forces. For example, there's a force due to the weight of this link, 349 Newton, and we're gonna resolve into two components, the one along the link and one perpendicular. The one along the link is gonna provide the compressive forces. Similarly, there's this force Fdy. It's also gonna have a component along this link, which is gonna provide a compressive load. Similarly, this force is gonna provide a compressive load. So I'm gonna write out the equation for the Fc. So basically, I'm doing a force balance along the direction of this link. So the first force, and I'm gonna assume this to be my positive along the link, and 43 degree to be my positive. So the first force is Fc, and then we're gonna have this force 349.6 sine 43, and then we're gonna have Fdy, which is 266.63 sine 43. Again, I'm only taking the component along the link, and then we are going to have a component due to the Fdx, which is minus, and then again minus 212, and this is the Fdx cos 43 is going to sum to 0, and if we solve this equation, we can find Fc to be about 265.22 Newton. And now we have the Fc. The other thing that we need to find is this thing ML5S1. So in order to do that, we just need to do a moment balance about this link, and we should be able to find ML5S1. So I'm going to do a moment balance. All right. So this is my final equation, looks like. And if you put in all the values and compute, it comes out to be about 122 Newton meter. And if you go back looking at this figure, you can also find Fm, because Fm is at a distance of 6 centimeters, the force to the muscle, and this is what balancing this force ML5S1. So you can compute that as well, and it comes out to be about 2 kilonewton.